Today we shall discuss regarding band pass filters. Here, a band pass filter has a pass band between two cutoff frequencies. That is, one is FH and one is FL. That is higher cutoff frequency and lower cutoff frequency. And the condition should be FH always should be greater than FL for the band pass filter. And if any input frequency outside this pass band, it is attenuated. And there are two types of pass band. One is wide band pass, and narrow band pass. And for the wide band pass, Q should be Q should be less than 10, and Q should be greater than 10 for the narrow band pass filter. Here, Q is a measure of selectivity. It is very higher the value of Q, then we call it as what? We call it as a more sensitive. Selective is the filter of narrower its bandwidth. Q equals to FC divided by bandwidth. So we know that bandwidth, we can write it as FH minus FL. FC divided by FH minus FL. Center frequency FC equals to square root of FH into FL. I already told FH is a high cutoff frequency and FL is a low cutoff frequency of the wideband pass filter. In narrow band pass filter, the output voltage peaks at the center frequency. Next, we shall come to the main types, that is wide band pass filter. So in this, we use both the first order and low pass filter and also the high pass filter, which are connected in series. So for example, to obtain a plus or minus 20 decibels per decade band pass, then we use first order high pass and first order low pass. If you want plus or minus 40 dB per decade, then we use a second order high pass filter and second order low pass filter are connected in what? It is connected in a series. And the condition FH greater than FL. So you can observe this is a that is a high pass filter section. First, what we have connected to the non-inverting terminal, we are giving input, okay. And this is the second part, that is first order low pass filter. Both are connected in series. And here you can observe the only feedback is resistance. For the both op-amp, only feedback is resistance. And the frequency response is like this. It is a stop band. From here to here, it is stop band. And from here to here, it is a pass band. And from here to here, it is a stop band. Okay. Next is a narrow band pass filter. So you can observe here only the for narrow band pass filter. So we are using a two feedback, that is C2 and R3. And here the input is given for the what? Here input is given for the inverting terminal. It is, we call it as a multiple feedback narrow band pass filter. So you can observe the figure frequency response of this narrow band filter. So this is the FC, center frequency. Okay. Filter uses only one op-amp. In this, both the cases, it is using only one op-amp. And sorry, in narrow band, we are using one op-amp, and in the wide band, we are using two op-amps. For the narrow band, we have some unique points, that is, it has two feedback paths. Hence the name multiple feedback filter. And op-amp is used in the inverting mode. If you observe, we have given the input for the inverting. Okay. And for the wideband, we have given the input for the non-inverting terminal. So from this, we shall choose the C1, C2 equals to C, and R1 equals to what we can write is Q divided by 2 pi FC into C into AF. R2 equals to Q divided by 2 pi FC into C, and AF can be written as 2Q square minus AF. Sorry, this is for the R2 and this is for R1 resistance. And for the R3 resistance equals to Q divided by pi FC into C. What is AF here? AF is a gain at FC, which is given by AF equals to R3 divided by 2 times of R1. And AF should be less than always 2 times, that is 2 into Q square. Advantage is here FC can be changed to a new frequency, that is FC dash, without changing the gain or bandwidth. So frequency, center frequency can be changed to a new frequency. We need not to change the gain or bandwidth. This can be accomplished by simply changing the R2 to R2 dash. R2 dash equals to R2 into FC divided by FC dash whole square. There is a problem. Design the band pass filter so that FC equals to 1 kilohertz, Q equals to 3, and AF equals to 10. And next, they have given change the center frequency to 1.5 kilohertz. That is 1 kilohertz to, it has been changed to FC dash 1.5 kilohertz, and keeping the AF and the bandwidth constant. So what we know that R1 equals to Q divided by 2 pi FC into C into AF. So we know that AF is 10 and Q is 3 and FC is at 1 kilohertz, and we need to consider C1 equals to C2 equals to C, that is 0.01 microfarad according to the figure what we have considered. So here, after substituting the values, R1 is getting the 4.77 kilo ohm. So similarly, you calculate R2 also. R2 formula is Q divided by 2 pi FC into C, 2Q square minus AF. Substitute and you will get the value is 5.97. And R3, Q divided by pi FC into C. So what you'll get 95.5 kilo ohm. But according to the standard values we have considered here is R1 4.7, R2 6.2, R3 100 kilo ohm. These are the standard values, which is near values we got. R2 dash 5 point. This is a R2 value. Okay, R2 value, and this is a FC value, and this value is FC dash. So we need to substitute and calculate the R2 dash. We are getting the 2.65 kilo ohm. So the standard is 2.7 kilo ohm. This is the design. Design a wide band pass filter having FL 600 Hz, FH 4 kHz, pass band gain of 6. Assume the capacitor value of high pass and low pass filter as 0.05 microfarad and 0.01 microfarad respectively. Draw the frequency response of the filter and also calculate the Q value of the filter. So here FH we have given C dash for the low pass filter we have considered, and FH equals to 1 divided by 2 pi R dash C dash. So for that R dash equals to 1 divided by 2 pi FH into C dash, we get that 3.9 kilo ohm. Similarly for the high pass filter, in detail we shall discuss regarding the high pass filter and low pass filter in further classes. Okay. FL equals to 600 Hz and C equals to 0.05 microfarad. They have given in the question, okay, 0.05 microfarad, and FL and FH they have only given in the question. So from that only I have considered R dash equals to 1 divided by 2 pi FL into C. So after calculating R dash we are getting 5.305 kilo ohm. So passband gain is equals to, they have given 6. AFT equals to A1 into A2, that is RF equals to 0.4142 R1. So we need to choose R1 equals to what? 10 kilo ohm. Here RF equals to 0.4142 into R1, that is R1 value is, we know that 10 kilo ohm. Substitute and calculate 4.142 kilo ohm. And bandwidth, calculate the bandwidth and center frequency and the Q value. After that, we need to find out the gain, okay, because we need to draw the frequency response for that. So you make a list that F in hertz, V naught divided by V in, and V naught divided by V in decibels, 20 log this value, okay. 20 log V naught divided by V in, if you calculate, you'll get in terms of decibels. So frequency is 10 hertz. So this is the formula how you'll get the V naught divided by V in value. So AFT they have given in the question only 6, and F divided by FL square root of 1 plus F divided by FL whole square, close bracket, 1 plus F divided by FH whole square, again close bracket. If you substitute and if you go on changing the value frequency, here you need to change the frequency value so that you'll get the V naught divided by V in values for different frequencies. And after calculating this value and 20 log this value, you will get in terms of decibels. Later you can draw according to that so that you will get the frequency response of this wideband pass filter. Next is a first order low pass filter, low pass Butterworth filter. Now what we have discussed is band pass, which includes wide band and also narrow. Now it is a first order low pass Butterworth filter. So we already know first order low pass filter circuit, right? So we have observed that V in, V1, V2 and RF feedback resistance R1 and this additional resistance potentiometer what we use, okay, and the capacitance. Here, first order low pass Butterworth filter, it uses RC network for filtering. And here, op-amp is used in the non-inverting configuration. You can observe this is a non-inverting configuration. Hence, it does not load down the RC network. And resistors R1 and RF, R1 and RF, which will determine the gain of the filter. And according to the voltage divider rule, voltage at the non-inverting terminal across capacitor, what we can write V1. V1 equals to minus JXC, minus JXC divided by our overall resistance R minus JXC into input source voltage. Okay, P in source voltage. So for output minus JXC divided by overall, that is R minus JXC. And here J we are considering square root of 1, and minus JXC we are considering that the value is 1 divided by J 2 pi FC. The XC value is 1 divided by 2 pi FC. So minus JXC, it is 1 divided by J 2 pi FC. After substituting and calculating, we get the equation like this. V1 equals to V in divided by 1 plus J 2 pi F into R into C. So this is the output voltage. Now what we have calculated is V1, okay, and output voltage. If we are connected for the non-inverting terminal, then 1 plus RF divided by R1 you'll get. If we are connected for the inverting terminal, minus RF divided by R1 you'll get. So for, we have connected for the non-inverting terminal 1 plus RF divided by R1 into V1. So we know the value of V1 that you substitute in this equation so that you'll get V naught divided by N equals to AF divided by 1 plus J into F divided by FH. So here AF is nothing but what? 1 plus RF divided by R1, that is pass band gain of the filter. And F is a frequency of the input signal, and FH is a 1 divided by 2 pi RC, that is high cutoff frequency of the filter. So FH, so we have replaced here 1 divided by 2 pi RC as FH. If you want to write in a polar form, then V naught divided by modulus of V naught divided by V in, that is equals to AF square root of 1 plus F divided by FH whole square. So that angle, if you want to calculate, phi equals to minus tan inverse of F divided by FH. Phi is nothing but a phase angle in degrees. And here the operation of the low pass filter can be verified from the gain magnitude equation at very low frequencies, that is F less than FH. So only at very low frequencies that the condition F less than FH, V naught divided by V in, that is equals to AF, and at F equals to FH, for that condition AF divided by square root of 2, and if it is F is greater than FH, then gain will be less than AF. AF is 0 to FH. So F equals to FH is a called cutoff frequency because the gain of the filter at this frequency is down by 3 decibels from 0 hertz. So if this is the condition F equals to FH, then we call it as a what? Cutoff frequency, because the gain of the filter here, gain of the filter has been reduced to what? It has been reduced from 0 hertz to 3 decibels. Okay, it is down by 3 decibels from 0 hertz. So cutoff frequency have minus 3 decibels frequency, break frequency, or it can be called it as a corner frequency. This is about the first order low pass filter. And next, how to design a low pass filter. First step is choose a value of high cutoff frequency, that is first we need to choose a FH value, high cutoff frequency, and next we need to select a value of what? We need to select a value of capacitance which should be less than or equal to 1 microfarad. So what is the first step in low pass filter design? First we need to consider the high cutoff frequency, that is FH, and next we need to select the capacitance value, and that should be less than or equal to 1 microfarad. It may be a mylar or tantum capacitors, or it may be a recommended for better. Why it is recommended means because for better performances. And next step is third step, calculate the value of R using what? Using the R equals to 1 divided by 2 pi FH into C. So first step is FH and second step is C. So we know the both values, and third step we need to calculate what? R value. Next, finally, select values of R1 and RF dependent on the desired pass band gain. So, how much the desired pass band gain, depending on that, we need to consider the R1 and RF values, and AF using a AF equals to 1 plus RF divided by R1. And next final is frequency scaling. Once a filter is designed, okay, now the filter design steps we have discussed. So now it is designed, they may sometimes be need to change its cutoff frequency. So now we want to change sometimes, after designing we want to change the cutoff frequency. Then the procedure used to convert an original cutoff frequency, that is we have already fixed, if we have already designed, but we want to convert the original frequency cutoff frequency to new cutoff frequency, that is FH dash. Okay, so to change a FH, multiply R or C, that is resistor or capacitance, but not both. Either you should multiply resistor or you should multiply capacitor. Not, you should not multiply simultaneously both. Okay, by the ratio of the original cutoff frequency to the new cutoff frequency. In filter design, the needed values of R and C are often not standard. and choose the standard values of capacitor and then calculate the value of resistor. In steps, we have discussed that we will choose the capacitance, then we will calculate the resistance value. That's why they are saying that choose a standard value of capacitor, then calculate the value of resistor for a desired cutoff frequency. This is because for a non-standard value of resistors, a potentiometer can be used. So problem based on low pass filter at cutoff frequency of 1 kilohertz with a pass band gain of 2. So the given FH has 1 kilohertz, C equals to 0.01 microfarad. If they are not given C value, you consider 0.01 microfarad. Okay. And R equals to 1 divided by 2 pi, that is 2 pi into 1 kilohertz into 10 to the power of minus 8. This is a C value. Okay, FH into C. So how much you are getting? 15.9 kilo ohm, and we can write it as R1 equals to RF equals to 10 kilo ohm. Since the passband gain is here, it is 2. Using the frequency scaling technique, convert the 1 kilohertz cutoff frequency of the low pass filter of problem 1 to a cutoff frequency of 1.6 kilohertz. What we have discussed in the frequency scaling. Now we have designed for the 1 kilohertz, but we need to change it to 1.6 kilohertz. So for that, what we need to do here, first original cutoff frequency 1 kilohertz divided by new cutoff frequency 1.6 kilohertz. What is the value we are getting? 0.625. So we need to multiply resistance for that. So what is the resistance value we got before that? R value 15.9. So multiply that. So you'll get the 9.94 kilo ohm. Use a standard value R equals to 10 kilo ohm. FH equals to what it will become? 1 divided by 2 pi R, that is R into C. So this is the C value and this is the R value. So what you'll get, that is new frequency 1.6 kilohertz. This is the what they asked in the question. Next, plot the frequency response of the low pass filter. So V naught divided by V in equals to AF divided by square root of 1 plus F divided by FH whole square. Fs is 2 and FH equals to 1 kilohertz. And input frequency, we change these values, and the gain magnitude V naught divided by V in, and magnitude in decibels, that is gain in decibels, 20 log V naught divided by V in. So this is the formula for that. Okay. If you go on changing these values, F values, okay, FH will be constant and AF will be constant. Only you need to change the value is F. Okay. If you go on changing the values of F, you'll get this different values. And for that, you need to calculate 20 log V naught divided by V in. Okay. In order to get in a decibels. So after calculating, you need to mark, okay, for 10, okay, for 10 frequency, how much we got that? 2, okay. And what about the in decibels? 6.02. So for 10, it is 6.02. And for the 100, how much it is? For 100, it is 5.98. Okay, for 100, it is 5.98. And for 1 kilo ohm, it is reduced. And for the 3000 minus 3.98, and again it is reduced for the 7000, for the 10,000, for the 10,000 it is minus 10.97, and for the 3000 it is minus 3.98. Some points you need to mark, and we'll come to know this pass band gain and stop band, okay, pass band and stop band. In first order low pass filter, first it will be constant and it will go on decreasing. That is the in first order low pass filter. In next class we shall discuss with the second order low pass filter, and still first order high pass filter and second order low pass filter.